Hey everyone, welcome to another episode of Robo Papers. Super glad to have Mengda and Han today with us. They are the authors from this paper called DexUMI, using human hand as the universal manipulation interface for dexterous manipulation. Thank you so much for making the time, guys. Maybe as a start, maybe Mengda, you can start first, talk about yourself, and then Han as well.
Yeah. First of all, thank you for inviting us. And my name is Mengda, and I'm a PhD student co-advised by Manuela and also Zhang. And during my PhD, my major interest on research is learning from human demonstration, including learning from human videos and also using different interface, and for example using skill as interface and also using flow as interface. And finally, this paper I'm using echo-scatter as interface. Yeah, this is my broad interest on research. Yeah.
Hi, I'm Han. I'm the incoming PhD student at Stanford University WE department and advised also by Shuran. And my major research interest is about developing the novel hardware and also combining the hardware and software power to bridge the gap, between the software algorithms and also hardware.
All right, awesome. Yeah. So thank you so much for making the time, guys. Maybe if we just to dive in, I know you guys have a short presentation. Maybe you can just use that as a start.
Yeah, sure. Let me share my
You can
screen.
share that.
Okay. So I will see the screen.
Yep. I can see the screen.
Yeah. So it's really my pleasure to present our most recent work, DexUMI, using human hand as the universal manipulation interface for texture manipulations. Yeah. So what is DexUMI? So DexUMI is a data collection and policy learning framework that allow humans use their hand as a natural interface to collect various manipulation skills. So how can we achieve that? So our key idea is, number one, we have a hardware interface, which is echo-scatter, to bridge the action gap between the human hand and the robot hand. And second is that we also have a software adoption layer to close the visual observation gap caused by using echo-scatter to collect data. Now, how about let's first talk about action gap and how we actually close that. So in DexUMI, our data collection device, echo-scatter, we actually share the same joint location and the limits as the target robot hand. And also, we share the same link length as the target robot hand as well. So basically, following these procedures, we are basically, based on the URDF, we can make this echo-scatter. And then at this point, you can really think about our echo-scatter is a version of robot hand, but without motors. However, if we're creating the echo-scatter in this way, completely following URDF, it often will cause collision between human cell and also the echo-scatter because they will compete for space. And we are actually struggling a lot at our initial design because, human cell almost cannot move the echo-scatter, right? And to resolve this, we actually came out with the idea is that how about we enter into an optimization loop that is we can move the thumb backward, right? As showing here, this is something after optimizations, and we actually can move the thumb actually backward by almost 5 centimeters. However, we can still keep the fingertip pose workspace same. So here we're actually making some trade-off, which is we actually want to, to move the thumb backward to improve wear abilities. The sacrification is that, the trade-off here is really that for some area which barely contact with the object, we actually don't care about that. But for the surface, it actually contact with the object a lot. For example, fingertips, we still try to keep its workspace same as original URDF. So here, I think it's a design choice we made to improve wear abilities while maintaining, the fingertip pose workspace. So I think this is how we actually design the echo-scatter, but designing itself is not sufficient for policy learning. We also have a set of rich sensor to capture the information sufficient for policy learning. So for example, we use the iPhone to capture the 6-stop risk actions. The reason we use the iPhone because it's very easy to use and we can directly use the AR kit from the iPhone to run the SLAM instead of in the UMI, they use GoPro. And sometimes you actually will get some troubles using GoPro to do this, to run the SLAM. So but the iPhone AR kit is really handy and we are really happy about that. We also use the wide angle camera to record visual observations. So the reason we use wide angle camera is something, design choice we are inherent from UMI. So because the fisheye camera can sufficiently capture, the enough observations for policy to influence the actions. And the reason we make it under the risk camera, because for the dexterous hand manipulations, most important things is actually to capture the interaction between the fingers and the objects. That's the reason we use wrist-mounted camera, and also it's a wide angle. So we further install the joint encoders at every actuated joint to record hand actions. So those joint encoders are really, really small, such that we can actually insert into our exoskeleton. And they are very precise. And finally, we also want to record some haptic feedback. That's the reason we also install tactile sensor on our exoskeleton. To avoid any embodiment gap between exoskeleton and target robot hand, we actually use the same type of tactile sensor as the target robot hand on our exoskeleton. So basically, DexUMI, we actually build exoskeleton for two different type of robot hand to show our generalization capabilities. We build the exoskeleton for inspired hand, which is under actuated hand, but we also build the exoskeleton for the X hand, which is a fully actuated hand. And you might already notice that, many design components has been shared across inspired hand and X hand. For example, we both have very similar, reverse camera mounting and also iPhone mountings. And we also, use the same type of joint encoders. And you can see many modules actually can be shared between inspired hand and X hand. So I think the takeaway here is that, let's say even we have a new robot hand comings, and you want us to design an exoskeleton, many components can be reused and shared from the existing designs. I think that this is really a good starting point for the other people to design their exoskeleton for their own dexterous hands.
So could I ask a couple questions here? So I think this is really interesting. One thing that's different about this from some other things that like some other like concurrent works, I guess, would be like a DexWild or what's the other one, Michael? But there's a couple of these that Ego Zero, so on. But like they are like you're actually doing a one-to-one kinematic map with the gripper, right? Like so everything is exactly so like this is exactly the same model as you deploy at test time. What are the implications of that from your point of view?
So let's say for the DexWild, I think I actually have a conversation with Tony. We actually have a mini conversation with Tony. So I think in general, I think DexWild, also previous work like DexCap from Chen, I think we actually are all trying to scale up the learning from the in the data. Right? I think we are all somehow on the same side. But I think there are still some difference between our works between DexWild and DexCap. So I think let's say for DexWild, they use some motion capture glove to capture the the human hand, and also they also have a wrist camera to capture the visual observations. But they still require some teleoperation data, and also it's the same for DexCap. DexCap also needs additional teleoperation data to correct the policy behaviors. But for us, DexUMI, so we really want, I will say it's zero shot. So basically what we really want is once we wear the DexUMI to collect data, we don't need any additional robot data, and we don't need any retargeting. Basically, we collect it, train it, and it can deploy it.
Yep.
I think that's the key difference between DexUMI and DexWild.
Do you think that results in better performance and everything like that, or do you think it's that makes sense?
Well, so in terms of like the final product, right?
Sure.
So I would say DexUMI is provides I would say a more clean solution. I would say because we actually don't
there's one less cause of error. I guess
exactly.
Is that the okay
exactly. And I also say data can be used in different pipeline, right? So let's say I think in general DexWild and DexCap they offer maybe their data, although it cannot be directly used for deployment, but they can definitely be used as pre-training. And I think pre-training right now is very popular, and people actually already found that pre-training actually can help the policy, a lot, even using simulation pre-training data. But for DexUMI, so I think we can not only train what will be used as pre-training, but if you really want to deploy it directly, you can also use it as train it with imitation learning policy. I think in terms of DexUMI, it's very scalable. Why? Because the overall cost, if you're excluding iPhone and camera, the overall cost is just like, the screw ends and just 3D printing material. And it's definitely under $100. And it's very easy to scale up. Yeah. And because we actually don't need additional teleoperation data.
Makes sense.
Yeah. Okay. Now, let's talk about the visual gap. So once we solve action gap, we actually have got a new problem. Why? Because as you can see, echo skeleton in the camera frame looks just quite different from robot in the camera frame, right? Although the shape is quite similar, but you can still see there's many details are different in the camera frame. And often we found that those details, if they are different during the training and deployment, the policy, although you can still roughly follow the right trajectory, for example, approaching the object, but it cannot finish very precise actions. For example, close the twitters in this case. Well, so
Sorry, Mengda, I have a question. Could you describe why would the robot observation be quite different from exoskeleton? Because I imagine, you basically fully control the mount for, let's say, the wrist camera, right? On both the exoskeleton and also on the robot. What leads to this experience in observation between the two? Presumably you use the same kind of camera and all that, right?
Yeah, definitely. So we're actually mounting the camera at the same locations and also, use the same type of camera. That's the reason you see from these two frames. So basically, the orange frame basically is what exoskeleton looks like from the camera mounted on the exoskeleton. And this is actually, what it looks like if it mounted on the robot hand. Yes, they definitely mounted on the same locations, but you can still see, right? For example, appearance is different, right? And there's many details are different.
Because we need to wear the exoskeleton.
Yeah, because we need to wear the exoskeleton. That's the reason. So basically, we wear the exoskeleton.
I see. So it's not so much the camera view is different. It's more just actually it's still not exactly like the Inspire hand. It's a bigger Inspire hand. Even though morphologically you're trying to copy as close as possible to Inspire hand. Okay, got it.
Exactly. Yeah.
Right.
Because
thanks.
Yeah, that's the reason we actually got the this visual observation gap. And our goal is trying to really to close or at least minimize this visual observation gap. And how do we actually achieve that? So we create a data processing pipeline. So recall that we install the joint encoder to record all the hand actions, right? Then basically we actually can replay the same action on target robot. So basically we actually can get a video of robot hand. And of course, here we are trying to replay it on target robot, but it's also very easily to be replaced by, say, you can train in a stable diffusion model, right? The input is the robot actions and output is the corresponding robot image. And this model can be easily trained because the data collection is very straightforward. You can just give the robot hand random action command and let it move there and record image. And this data set is very easily to obtain, and you can train a stable diffusion to replace these steps. But for now, for simplicity, we simply replace the same action on target robot hand. Okay, then next, we use the SAM2. Segmented and tracked, number one, the exoskeleton mask in the exoskeleton data. And we also use SAM2 to segment out the robot hand mask. And the things we actually need to do first is to get a clean background. So in order to get that, we do something on the exoskeleton video. So basically, we use the flow-based inpainting method, which takes the previous steps, segmented exoskeleton mask as input and output a clean background videos. So basically, we are using flow-based inpainting. So what it does is that it will warp the pixels from the other frames to the current frame to fill in the missing part, which is the exoskeleton, and it will replace the exoskeleton pixel with the background pixel. That's the reason you actually can see this impinting cost is quite high. Okay, and I also want to mention that both SAM2 and impinting does not need any fine tuning. It just can be run out of box. Okay, now here's actually one very interesting part. So how do we actually get the robot hand visible mask? Because imagine, right, you actually when robot hand or our exoskeleton is interacting with the object, some part of the fingers will be occluded by the object, right? And one very, very naive solution is that we can simply copy, the corresponding robot pixels over the background. Then it actually will cause problem because it cannot maintain the proper occlusion relationship. So our goal here is really, it should be compute what's the actual pixel is visible from the camera frame based on the relationship between object and hand. So our solution is actually quite simple. So basically, we are taking the intersection between the echo scatter mask, which is in orange, and the robot hand mask, which is in blue. So basically, you can see the green part is the intersection between these two masks, right? And you actually can see that there's a small blue part here, which is indicating this part is being occluded. So whatever is in the intersection part, it should be visible. Okay, so basically by this, we actually can compute robot visible mask. And as you can see, so we can apply this mask over the actual robot hand pixels to get which part of area pixel is actually visible. Now, the last step is super simple. We simply copy the visible robot mask over the background, right? And we can actually get a very high fidelity robot hand demonstration videos. So basically, you can see we actually use off-the-shelf computer vision model, including 7.2 and ProPincher, which is a flow-based painting method. And we start from an echo scattering video. And as we discussed before, human is wearing echo scattering. And that's the reason you can see there's actually a green glove here and the visual, and it looks quite different from the final robot hand. And we start from here. And we actually can reach here. So basically, this is a data processing pipeline we create to convert an echo scattering video into a robot hand videos. And basically, we can use this video as the training input, which is visual observation input into the policy to ensure there's really very small gap between the training and deployment. Okay, so
Do you need to do any further augmentation or anything? Sorry.
definitely, that's a great question. Yes, we definitely add a lot of augmentations in the training. Why? Because as you can see, you might already notice that that's something we cannot fix.
Yeah.
Number one is that for example, the lighting is different, right? Because when you actually teleoperation, let's say you actually teleoperation or robot hand is interacting with the object, the lighting condition can be quite different. So number one, we are definitely add, for example, like a random grayscale, and also the random augmentation, for example, color jittering.
Yeah.
And also even some Gaussian blur on the visual input. The reason we add some Gaussian blur because we are using the flow-based painting. And you might already notice that the background image, there are some areas a little bit blurred because it has been painted. And to make the policy is less sensitive to those blur area, and we add some like a Gaussian blur on top of the image during the training.
Got it. Okay.
Yes, I think that's a great question. We definitely add many, data augmentation. Yeah, even after we finish this, even after we apply this data.
How about the touch sensor? So far, what you described is purely computer vision, right?
Yeah, it's just a pure vision. Yeah. So in terms of the tactile sensor, because as we mentioned before, we're actually using the same type of tactile sensor as target robot hand. So for example, here, what I'm showing here is an X hand. So you can see X hand actually has, so each finger got some tactile sensor. And we actually install the same type of tactile sensor on our echo scatter to make sure there's no embodiment gap. However, but I think that's actually, one thing that I do want to mention, because human hands are very powerful, right? And this actually will cause some slightly embodiment gap. Why? Because human hand is more powerful than robot hand. So when we actually manipulating with object, it will, using a lot of force. And sometimes for most of the tactile sensor, if you apply a very large force on tactile sensor, it actually requires some time to restoring. Yeah. And however, we didn't observe that in X hand if we only trying to teleoperate data. Because if we teleoperate and collect data, because the robot hand has less force than a human hand. So the restoring process for tactile sensor is way more quick, is very quick. I think that's something, we do. That's some small embodiment gap. And to overcome that, we actually to apply some threshold on the tactile sensor reading to, make it become binary, either contact or non-contact. I think this is something we really hope we can do better for the DexUMI project. Yeah, but for now, I think this is really, I will say, a quick solution to to close close the gap on the tactile sensor.
Yeah. Actually, I wanted to. My question was like, how do you use the tactile sensors during the actual deployment? Well,
Oh, I see.
versus also when, because the technique you described are all computer vision based, right? So I'm curious how you are using the tactile sensors.
Oh, I see. I still asked a question. Sorry. Yeah. So basically,
No worries, yep.
so our policy takes two types of data as input. The first one is the visual input, which we just discussed, and the second type of information is tactile information. So basically, we install tactile sensor on the exoskeleton during the data collection, right? So we install tactile sensor on the thumb and also the index and also the middle. So basically, we record the tactile reading from these three sensors and also make it a part of the policy input. During training, the policy receive the tactile sensor information and also the visual observation and output actions. Okay, this is training. And during inference, we are also reading the tactile reading from the actual target robot hand, which is X hand. And also, because we also have the camera looking at placed at the same locations, we also passing the visual observation as policy input and output actions. Yeah, that's how we actually use the tactile sensor.
Got it.
And finally, we evaluate our system on two different robot hands. One in spine hand, the other one is on X hand, over 5 different tasks. So in order to complete those tasks, it actually requires our system to learn precise, context-rich, and also long-horizon manipulation skills. So as you can see, we actually evaluate on many different tasks, which require a lot of dexterity. Our final success rate is around 86%, and this is without any retargeting and without any additional robot teleoperation data. And we have already fully open source our code, CAD, and including very detailed assembling guide on our project website. Yeah, I think that's it's
Awesome.
a very quick introduction on DexUMI.
Very cool.
Yeah. Well, firstly, thanks for open sourcing everything. Yeah, it's. I think the community will definitely pick it up and build on top of it. I'm curious, like, so for these, I guess evaluation, right? How many demos did you try to do with the exoskeleton before you actually, and then to go and test and get your 80% success rate?
Yeah, so I think that's a great question. So different tasks actually require different number of demonstrations. So for example, for cube picking and add carton opening, I think we only roughly collect around 200 and 300 data trajectories. And for T picking with tool, I would say this one is really challenging because you can see it's a task with like different subtasks, right? It first need to grasp the tweeters, right? And then move the tweeter over the T port and close it. Then finally release the T into the cup, right? This is a very long horizon task. And for this task, we actually eventually collect roughly 400, even 500. I think roughly between 400 and 500. Yeah, the trajectories make it to reach very high success rate. And for kitchen manipulations, roughly also in the magnitude of 400. And we also collect some, we call it stage data. So for when we say stage data is that we only collect the demonstration for a subtask. So for example, close the knob, as the first step, we collect actually additional 100 stage data. But on average, I would say of kitchen manipulations, we in total also collect roughly 400. So basically for all the tasks, the magnitude is around 300 between 500. Yeah.
But I suppose in your study this time, it's the place where you collect the data is also where you test, right? So you didn't, yeah. Actually, there's a very good video I thought on your website. I don't know whether you have in your slides where you show the difference in time required to collect using yeah. If you get that video, I thought that was a very compelling case of why something like DexUMI will make sense.
I'm assuming you are talking about
this one. Yeah, this one.
Yeah, let me play it. Sorry, the internet might be a little bit slow, but
so,
let me explain. So here, I'm really trying to compare how to use different way to collect data. The first way is teleoperations, and you might already noticing we're actually using our exoskeleton to do teleoperations. So that's nothing prevent us to doing that. And also, second way is DexUMI, and of course, we also want to compare, how efficient to using the bare human hand. And as you can see here, using DexUMI, let's say even in terms of times, right, we can finish this task only just in 7 seconds, very close to the bare hand. In terms of teleoperation, actually require like almost 26 seconds, which is less efficient than DexUMI. So this is number one in terms of like efficiency. You can see I'm very carefully trying to, changing my point of view, right? It's kind of like I'm moving my own camera in order to see whether I'm making contact with the T while I'm doing teleoperations. So this is the second aspect for teleoperation data. We often need to, to change our point of view in order to see whether we have making contact and whether we are making the right operations. But for DexUMI, because we're really wiring it to collect data, right? And so it's really, very nature. So we often see, every all information. Just we don't actually need to moving our hand around. So I think that's kind of best.
So in your view, in this case, at least between the teleoperation DexUMI, is there anything that you think teleoperation has any kind of pros over DexUMI? Or you think absolutely just like...
Yeah, okay. So that's how about I actually had another point on why DexUMI is better than teleoperation. Maybe I can finish that. Then I'll talk about.
Oh yeah, of course.
And third point is that it's about force feedback. So as you can see, right? So at the end, I actually, while I'm trying to release the T, the trigger actually, it's not cannot keep straight. Why? Because I actually cannot feel what's the force on the fingertips. Right? It's very hard to control. But for DexUMI, because I can get very direct haptic feedback, so I actually can, make the, keep the trigger straight. I think this is the third advantage of DexUMI, which can get, force feedback. So typically people actually need to build, additional device to get the force feedback. For example, Han has another word called do glove, and it actually has a force feedback. Yeah. Okay. So in terms of, when actually teleoperation is better than DexUMI, I think that's also a great question. So I think this question is not only about DexUMI, but also like widely on UMI data, right? Because people often ask like, what's the difference between how you compare teleoperation with UMI data? So I think it's the same. So basically, there's still some, I would say, difference between teleoperation and UMI data. In UMI data, either in DexUMI or UMI, state and action, the concept sometimes is really close. And in teleoperation, state and action are often different. So why I'm saying that? So let's say when you're using space mouse to teleoperate, let's say for example, you are your robot arm, right? So your target actions or target joint or target like end effector locations sometimes is not the same as your current robot end effector locations. But for DexUMI or UMI data, state is action and action is state. Sometimes it's very close. And I think this is something key difference when we actually, when we compare in the teleoperation and UMI-like data. And how does that impact policy? I think it's majorly on, when we're making contact with the object. So thinking about we are trying to grasping something, right? And if we directly record, let's say if we are using UMI, right? And this is like we can record the locations and the location of the motor of these two fingers, and we record it. And let's say we are not even trying to replay it, or we're not trying to use it to learn a policy, which is replay, because we only and this is most likely the contact is very subtle. That may not can be say very tightly to grasp the object, because here state is really the action really state. But let's assume is teleoperation. Human often, try to overshoot. It will try to, grasp like, more. And we actually will reflect that overshoot when we teleoperation. And here, even though, let's say the cup does not deform, right? And the joint and the location and the motor position is same, but the teleoperation command is often overshoot. And this is actually a second key. I think this is how actually impact the policy.
So this is perceptual aliasing, I guess, that you're describing. That like in these cases, it's just much more. Is that kind of what you're getting at here?
Yeah, I will say
like the fact that basically because these state and action spaces are the same, it's gonna that makes sense. Okay, yeah.
I'm curious if you because I suppose you are I mean, with something like DexUMI, you are fully relying, I suppose, the AR kit, the SLAM from AR kit to infer 3D space. Whereas presumably with teleop, you know all the joint position of the actual, robotic arm. Is there a difference, you think, or this days SLAM is just so good that
Well,
it's almost like a direct replacement? Does it matter?
so I would say Apple really do a good job here. They are AR kits. Well, actually, in another project in our lab, in our labs, they actually test, how accurate iPhone SLAM. The way they test it is by putting iPhone in a mocap room, because mocap is always very accurate. So the ability, they treat the mocap data as the ground truth, and the iPhone AR kit, and compare the iPhone AR kit, the trajectory they record with with the mocap data, and the error is really, really small. So I think iPhone really, I think is doing amazing here, the AR kit.
Got it. But do you think that the small difference over time will accumulate?
Definitely. It will definitely accumulate. However, I think because eventually it is a learn policy, and we found a learn policy actually, because it is more reactive, and sometimes it won't be so sensitive to this drifting.
Yeah, I suppose if your task is quite short, like let's say in this instance, 7 seconds you're done, probably the drift doesn't matter as much.
Yeah, but I think it might cause problem if if we record, for example, very long times, and it might drift. And also the other things we found constantly is that if we record too long, and it might overheat. Yeah, and I think once it overheat, I think it will drop the frequency. Yeah, I think this is another issue we found. Yeah, for iPhone AR kit. But otherwise, I don't think we have anything to complain. Yeah, iPhone AR kit can really provide a very accurate, SLAM. Yeah.
Yeah, we Chris and I have been talking to obviously a bunch other researchers, and it seems to be a common thing now. Everyone is using just AR kit as a default SLAM solution. Just get it out of the box. Yeah, I'm also curious. Sorry, Chris, I keep asking. Actually, please ask. I'm curious. How do you explain the difference between the 2 seconds between, let's say, bare human hand and let's say DexUMI?
Yeah, I was gonna ask that.
Yeah. How about Han? Maybe you can answer this question. Why? What's the 2 seconds? Why that's still like DexUMI is slower 2 seconds than a human?
Experience is that when you wearing the exoskeleton, you will feel somehow it's not that natural as your bare hand. You will you'll concentrate on whether you open your hand enough to like cover the object, and whether you contact the object properly, whether you since you can't use your own fingertip to like interact with the object, so you'll guess if I apply enough force on the object to grasp it on. So all of this just comes to the 2 seconds.
And also, the other point I want to add is that the reason we build exoskeleton is really try to constrain human hand, right? And because human hand is so flexible, but compared to robot hand, right? Robot hand has this degree of freedom and this range of motions. So when DexUMI exoskeleton is definitely trying to constrain human flexibilities, and because we are actually using kind of like a downgrade version of our hand, trying to do something.
It's
right?
like you handicap the human hand a little bit.
That's actually can explain why that's 2 seconds. And also, what I had also said, we actually need to think about whether we have actually contact with object, whether it's tight enough. It's also add something. Yeah.
Do you think with practice the gap would get down to near zero? Like, because clearly with the teleop case it wouldn't, because the camera's in a different place. Like you're missing information, but you're not missing information here. So, and people can get really good at using tools. So what do you think?
Well, you are missing information from touch, right? I mean, you have visual.
Oh, a little bit, I guess. You saw some. Yeah.
I think that's a big one. I mean, if you cannot, if you can't see at all, then you basically have no idea. Whereas, like I can put behind my back like this, and it's purely based on touch, right?
How much can you feel through the armature, through the glove?
Oh, yeah, maybe Can you feel, do you think, through the exoskeleton?
We can definitely feel. I think this is the one huge advantage of our approach, because so once we are exoskeleton and we're making contact with the object, the haptic feedback is very, very strong. It's so obvious whether we have making contact with the object or not.
I see. So the I mean, when you were wearing the exoskeleton, I mean, the all these like haptic sensors, right? So when I touch the object, how do I feel? I mean, I feel it through just my fingertip pressing against the sensor, right? That's how.
Yeah, so you actually get to the feeling from your fingertips making contact with exoskeleton. And your exoskeleton is making contact with object.
see.
Okay, actually, we
I
actually
see.
have an exoskeleton here, so maybe we can explain better.
There you go. Okay.
All right,
I was
so
gonna ask.
maybe hand,
Yeah.
you can, I can wait. Oh, so let me wait.
Wow.
No,
Okay, this is good.
We can wait. Okay. Maybe we can just use the index finger. Yeah. So okay, so let's say we try to touch this iPhone, right? Okay, and when the index is making or any finger making contact with the iPhone, so basically it's exoskeleton with making contact with iPhone, and there will be some force feedback. First, will pass to the exoskeleton because your fingertips is also making contact with exoskeleton. Then this feedback will also pass to your fingertips. So it's kind of like it's passing the force information through the exoskeleton. Yeah.
I see.
This-
Yeah, but very interesting. I suppose like your teammates in the lab, a bunch of you have tried using this, and all of you have kind of different hand sizes.
Yeah,
in terms of the UX, how's the experience like for folks with, I don't know, longer fingers, fatter fingers, thinner fingers?
Well, I think that's also a great question. So, in short, for me, I feel okay because I really have long fingers. But for hand sometimes feel it's a little bit hard to operate on the exoskeletons. So to your point, it definitely wearability, whether you feel comfortable or not, is definitely depend on your hand size. Yeah.
I have a sorry, Han. Yeah.
I want to add one more point. It's about our design of the finger cap. You can slightly change the length and also the width of the finger cap to make yourself feel more comfortable. But I would say, yes, it could increase some kind of wearability, but still it was not that comfortable.
Yeah. Presumably there are limits just because of the kinematics that it has to. Yeah. Okay. Makes sense.
Got it. I do have another question about like the. Okay, so when you are using DexUMI, right? You as a human, you can move your neck around and your head around, so you have like privileged information that ultimately when you train your policy, presumably it's all just from the iPhone and that wrist camera. No, not even the iPhone, right? It's only the wrist camera, right? I'm right?
Only the wrist camera. Yes.
So, how do you think the policy can ever be better than like it's do you think it translates directly because the human in this case is in your case you look like you're leaning forward.
I think that's a great question. Yeah, I think that's a great question. That's the reason we use fisheye camera. So the fisheye camera really can capture very wide angle, right? So it's kind of like we want to capture as much as information as possible from one single camera. I think this is my answer to your question. This is only the first part. And second part is, yes, I think this is another research directions our group, which is Zhang's group is exploring right now, is active perceptions. Really, like we have a paper called like moving neck, like vision actions. But in that paper, I think Zhang and Hao Yu is actually exploring that whether they can mount the camera on a robot neck. And the robot neck actually can move. So basically, it's also trying to kind of like choose the camera view in order to better making manipulations. And this is something we also want to add as a follow-up for DexUMI in the future. So for example, we can always have a head-mounted camera and we can do the manipulations. So for the policy input, not only the wrist-mounted camera, but also the head-mounted camera. We can also add additional input to see more information.
Does that mean you're going to build an armature exoskeleton for your neck so that to force you to obey the robot's kinematics there too?
I would say that's a not bad idea. Maybe we can get to like a whole body UMI. Maybe.
Yeah. Okay. Yeah. I've always felt like this was probably. I've always felt like that was probably the biggest actual advantage because we were talking about this earlier of a teleoperation system though, was that it actually forced you to use the actual sensors on the robot, or it could, not in this case, but yeah. Michael, did you have a question? I have another one, but it's going to be pretty unrelated.
Yeah, I mean, I'm curious what you guys think. So I guess that I guess if you look at a dimension, your teleoperation, which we use a physical robot, and then in your case, you have an exoskeleton here that kind of handicap the human body a little bit, but then conform to the exact, robotic, like and robotic, let's say X hand or Inspire hand, right? So that it's so-called retarget a lot better, right? How about what do you think of projects like let's say, from Meta area glasses, where you just totally free form and you just like use hand pose estimation, that sort of stuff, and you get the benefit of like your camera is already at the head, so you get that view. Because presumably like that is way more like even natural for a human. I guess that would be a bare human hand case. What do you think of that kind of approach? I don't know whether you guys saw the paper. Like
Yeah,
there's one recently called Ego Zero.
I think it's also a very promising research directions. I can definitely see the benefit of using Meta's glasses or using Apple's Vision Pro to record data. And also, I think there's many papers recently. So, for example, Xiaolong also has some paper. How to combine the human data as pre-training, and also some co-training paper. Also, there's also some co-training papers. I think again, it's really about how to use data properly, right? So, for example, the bare human data with, for example, recording with the AR glasses, we can always use it as a pre-training phase. And it's very powerful, right? And many paper has already report, for example, also in the DexUMI, right? Co-training with human, human data actually can improve the performance a lot. I think the pre-training phase is really, really important. And we also need data for the, for example, post-training, right? So for post-training, we actually need very high quality data. And in this case, maybe DexUMI or even teleoperation data can be very, very useful. I think in general, I feel like all kind of data source is useful because, robotics, we don't have data. So
Yeah.
we count on every bit of data. Count on every bit of data, right? So there's no bad data. We just need to find the right place to put data in. Either pre-training, post-training, we just need to find the right place. We want to use every data, and of course, with some good quality.
Yeah,
That's great.
I mean, I totally agree on this. I think this makes a lot of sense. So, I was gonna I was gonna ask about the fisheye camera setup. Do you think that has any implications for pre-training for you guys? Because for versus post-training, like the fact that your camera looks so much less like all this web skill data people are grabbing, or is that going to be an issue, or do you think it doesn't seem to matter?
Yeah, it could be an issue. Yeah, because as you mentioned, especially for internet level data, that's not apparently not too many fisheye camera, right?
Sure.
But I will say that's the reason, maybe in the future we can add head-mounted camera, because once we have a head-mounted camera as a policy input, this is very similar to the egocentric videos. For example, a lot of data sets has been released by Meta. Also recently, Apple also released their egocentric data set, and this data set can really be maybe they can find some connection between. Yeah,
I had one other question that goes way back to something we were talking about earlier that's been bothering me though. So this is about the SLAM thing. So you were talking about how if you did a really long trajectory, you thought it would drift and would cause things to and it might cause performance issues. And that kind of surprised me because I actually thought that shouldn't matter unless I misunderstood how your things worked. I thought all the actions were relative poses. So then shouldn't it self-correct? When you're actually learning it, or if you only care about local correctness?
Oh, that's actually a great question. Yes, we use relative actions. So even there's a drift, I think it will have very, very minimal impact on our policy because we always calculate the actions as a relative. Basically, when we say relative actions, what's my current actions compared to maybe 16 frames before? It doesn't matter whether at the beginning of the trajectory. It's only care about, for example, 16 steps before. So it may have very minimal impact. I think that's a really good question.
That's what I would hope, right? If everything's visually obvious, the drift should only matter if you don't have features to refer to, right? I don't know. Okay, that makes sense. Cool. Yeah. Thanks.
Thanks for the question. Yeah.
All right. If you had some extra time to write the paper, so a good time to talk about what the future work would have been. Yeah, what future work you want to do.
Yeah, sure. So maybe you can talk about one thing we think about the final version of DexUMI, the co-design.
Yeah, because currently we are constraining human range of motion because we just have 12 degrees freedom for the dexterous hand. So what if we can first design a comfortable exoskeleton? Let's say human could wear that and easily manipulate with object. And then considering that design, we design the related dexterous hand. So that's what we call it co-design.
So I think this is something we really wish to do if we have time. So as I mentioned, we are really trying to make the exoskeleton for target robot hand. And those target robot hand is not made for DexUMI. So basically, if we can do co-design, we actually can, improve wearability a lot. And also, have all the advantage of DexUMI. Yeah, this is something we really want to do in the future.
You mean co-design,
think you
meaning
could- you-
actually design the robotic hand as well?
Yes. Yes.
Interesting.
So we are really excited about this idea. So if we ask ourselves, like, what's the ideal hand for DexUMI system, right? First, DexUMI is really about data collections. Right? Basically, we want to optimize the human's wearability when we collect data. Then that's the reason we propose to make an exoskeleton the human can wear very comfortably, to fine-tune the joint locations, link lengths, etc. And based on those parameters, we reverse design and robot hand.
So like this would be like reverse designing it so that it'd be comfortable for a wide range of like hand sizes and body shapes and all of that. Okay, that's cool.
Yeah, I'm curious if you think that endeavor is require. It seems to me will require a lot of like actual manufacturing, like know-how and things like that. I would love to see an open source that is as good as, I don't know, some of these manufacturers like X Hand, Inspire Hand. But please do. If you guys can actually do
I feel
it.
like for the Inspire hand at least, there's some good open source, like the Leap hand or the Ruka hand or and all these. Like you can do some pretty cool stuff with open source these days, right?
Yeah, definitely. So I actually, watched the Ruka Hands presentation today. I think they did some amazing. They actually open source, keyboard driven. And also I also mentioned, the Kenny at Carnegie Mellon, like, he also got the Leap hand and he already has V between the V3. They are all very amazing work. And I actually we observe, there's more like amazing project, across like academia. They are open sourcing a lot of things, including texture hands, something, really complex. And previously we think it's very hard for academia to make. And we actually saw many effort and their product is amazing.
Yeah. There's also the new one from Hugging Face, which I forget the name of, unfortunately. But there's an incredible amount of open source hardware these days, it seems like.
Yeah. So I think, I will feel like, maybe in the future, data collection can be crowdsourcing, so everybody use a 3D printer, or maybe, company can send some exoskeleton or OMI device to people are really willing to collect data, and everyone can custom data. We can scale up robot data very quickly. I think Hugging Face is something, is doing something similar, right? Yeah. Then data is the key, at least for now, to make robotics, can become better, I would say.
Yeah, absolutely.
Yeah. Okay, cool. So I guess to kind of wrap things up, I think you guys already kind of mentioned like if you guys were to given a bit more time, what kind of directions. I didn't quite expect you guys are thinking about co-training, but I think that would be super cool. Basically, instead of forcing the humans to match the existing hands and basically change the hand to kind of meet halfway, right, between the human hands and the robot hands. Yeah, so I guess is there, this is a usual last question we like to ask. Are there any like papers that you come across recently that that you thought was like really interesting, you want to give a shout out to? Doesn't have to be like robotic hands and whatnot. It could be anything.
Sure. Yeah. Han, maybe, do you have anything in your mind?
It's all about hardware demos I saw today on workshop. Yeah, it's maybe not the full papers. Today at our RSS workshop, I saw some cool hardware demos. One is from MIT Pocket Lab. They designed a 2 degrees of freedom robot wrist that basically, if you don't have the wrist, just a 6-off arm, the range of motion is relatively limited. But if you add 2 more degrees of freedom on the wrist, you can do something like this. So it's benefit the manipulation. And they design actually that's the point. They design a relatively complex mechanism and then open source everything. Appreciate their work. And also a tactile sensor from Binghao. It's in Juice Lab. They design it. Yeah, that paper. Actually, they upgrade their tactile sensor, so you can make this tactile sensor array in a very low cost, and they also open source everything. So you get that thin film, and you can get the tactile image from that array. So that's the current hardware paper I read.
Yeah.
What are the names of those papers?
Do you remember it? I think for the intro paper, I remember it's 3D Vitex.
Yeah, Vitex. Yeah.
3D Vitex. So let me search right now. Is that this one?
Yeah.
Yeah, I think it's a really low cost, touch sensor. Yeah, I think this is what I'm referring. Yeah,
Pretty cool.
and also
Yeah,
the
I
other
really
paper,
like. Yep, sorry. No,
Yeah.
I say I really like all this. Like you said, there's a wave of this, more like research-driven hardware that are open source.
Yeah,
it's
the
a
other
great
project
great trend to see.
Yeah, I feel quite amazing. It's also from our lab. So it's a robot snake. So basically, the reason I feel so interesting because it actually have a number one, it's a robot snake, and number two, they actually install so many cameras on this snake. If I remember correctly, it's like 21 cameras. They actually have 21 cameras on it. Yeah, it's almost like try to use not only the whole body dexterity, but also the whole body vision. Yeah, I also feel like this paper is quite interesting.
It's like a snake with eyes around the whole body.
Yeah, exactly.
Yeah, no need to be limited by the human form, right?
Yeah, this also I think Zhang always mention something why the robot need to be similar to human, right? I think this is something question Zhang always ask because potentially robot can be superhuman, and also also for the dexterous hand. Right? So why every dexterous hand need to be like human hand, right? It can be better than human hand.
Better than human hand, though. How will you use DexUMI?
Yeah, that's the story. But in general, the robot don't need to be like human. It can be superhuman.
Actually, I just realized I have one question about DexUMI. If we go back a little bit, I'm curious, you put one camera. Why don't put another camera? I mean, it's because you go with very wide view. Why don't you just put another camera and maybe have a little bit of stereo thing going on?
This is another thing. If we have time, we can do that.
Okay, got it. Makes sense. Okay, cool.
Definitely
cool.
more. I love more camera. We love more camera. Yeah, because camera right now is key.
Yeah, but I'm curious about a setup actually. I see for some of your video you have all these wires going through, tip around, and so what are those wires all ultimately going to? Is it a somewhat portable thing that the human can just go around and just do stuff?
Yeah, we can definitely do that. Just for the first version, because we insert the joint encoder inside each joint. So we connect a cable to connect the joint encoder to the circuit board, and also power on the circuit board and streaming the data from the board to the laptop. Right? But for the future work, we can substitute these cable with a FPC, a very, very small cables, and also design the circuit board. Currently, we are using a baseboard with all headers on the board, and you just plug and place the modules. So in the future work, we could just design the circuit to make it very compact and small, and just insert it into our skeleton. And also for the data streaming part, actually you can take the power from the iPhone and also streaming the data to the iPhone so that you can make it portable. Not doable, just engineering effort.
And probably the iPhone will overheat even faster. But okay, we'll let Apple solve it for us, right? They will magically make it go away. Okay, that's awesome. Well, anyway, thanks for making the time, Mengda and Han. I think really fascinating project. And as you guys know, I actually tried messing it with the project. I think, just because you guys open source everything, I think the community is just going to experiment and build on top. Yeah, so I guess that's a wrap, Chris, or maybe Mengda and Han. Any final words you guys want to say?
Well, thank you for having us. We really have fun here, and we really enjoy the conversation between you and us. I think a lot of questions is also quite inspiring. for us, and to think about, why not, adding more cameras and,
Yeah.
why not, just, do something like, it's really, really amazing to have such conversations. Yeah.
Well, the
Thanks.
pleasure is ours. So anyway, okay, cool. Looking forward to your next paper then.
Yeah.
Right.
All right.
Thanks for coming.
Okay. Yep. Okay.
Hey.
All right, Chris. What did you learn today?
So what I really like about this stuff of DexUMI compared to some of the other things that we've looked at is that it is like the gripper's like a actual one-to-one match with the robot, which like as you say means that you can just use it on the robot. You don't need to do it's in a way simpler, right? Like the hardware's more complicated. You got this fancy piece of hardware, but it's such a simple way to teach robots quickly because you can just kind of like build this thing, matches exactly what the robot's capable of, and do it. And if you can get that alignment perfect, then it just works. So I think there's something very nice about that for getting high quality data really fast. Yeah. What do you think?
Yeah, I think it's definitely a very good direction to go down. I mean, if you look at the cost of this thing, it's like so cheap. A couple
Plus an iPhone, but yeah.
But you're talking about iPhone. I think if I'm not iPhone 12 onwards already have decent AR kit support.
That's right. Yeah.
So you're talking about a few year old iPhone, which resale value is very cheap. Even for so I think so I don't think the iPhone is necessary even a bottleneck. And iPhone obviously you can use it as a normal iPhone, right? So it has value. It's
another
not like
value
you're buying
too,
a
yeah.
separate thing only to do this, right? So
Right.
I don't think that's a showstopper. Yeah, and I guess it's interesting. We just did this episode right after we talked to the guys from Eco Zero. So different
And
trade-offs.
Dex Wild.
But
and right, we did.
and that's
we
why,
have-
oh my gosh, yeah, we talked
We
about
have
this.
done
Like,
three
it's all
very
back to
similar
back.
things in 3 days.
Yeah.
So,
And they all have different trade-offs, and I see it as like I mean it's okay to debate about trade-offs in a podcast format like this and just kind of push the limit to find out what the pros and cons of all this. But ultimately, I think like what Mengda said, we're so lack of data in robotics. Just go and try to scale up the data instead of trying to worry which data is more useful. Like we are not even in the optimization
Right.
space yet. Like
Well,
I feel
yeah.
that let's just
Right. I mean, another point that he was making, which I think I agree with, is that there's always going to be a role for different quality levels of data. So like if you can collect a lot of data with a hand, even if like there's a lot of possible failure points in all these things, like with a separate hand model, right? Because either you need real robot data or whatever it is, right? Or like you have a calibration step that can potentially introduce error or like retargeting. But like, okay, so say I have a huge pool of slightly less data and I use that for pre-training, and then I have these much more expensive like exoskeletons that I use for data collection, much more expensive, meaning just they take a lot more effort to build, right? Like, so I can't do as much of that, but that's okay because I use that for fine tuning, post training, whatever you want to call it, right? And that's so there are different types of data that can all be used for different things, and as you're saying, like it's just the goal should just be to get lots and lots of interesting data.
Yeah, for sure. And I really like that. What was surprising to me towards the end was that they're thinking about co-design, like basically changing, literally redesigning the robotic hand instead of trying to force a human to something that it's an existing hand that is not necessarily built with like a DexUMI kind of like end use case in mind. So I thought that's also a very bold take on things.
Yeah, I really like that. I think it has so much potential for like improving the pain points of this method. Like you can build a much better X armature that like is more comfortable and easy to use and better fits tactile sensors and multiple all that kind of stuff. Yeah,
for sure. Exciting stuff, man. Yeah.
Yeah.
Okay, cool. I guess to the
Awesome.
next one. All right.
Yeah.
See you soon.
See